For nearly a century, we've lived with one simple rule. Nothing travels faster than light. It's the universe's ultimate speed limit, the bedrock of modern physics. But what if that's not the whole story? What if the information that makes an object what it is could be sent from one place to another, instantly, without crossing the space in between? This isn't a thought experiment anymore. After chasing a quantum puzzle for 25 years, scientists in Japan have achieved a feat that is a critical stepping stone towards teleportation, something many thought was impossible. They didn't move a particle. They figured out how to identify a complex, interconnected system. It's not science fiction anymore. It's the first page in a new chapter of technology, where we're learning to use the universe's strangest rules in ways we never thought possible. In September of 2025, in labs at Kyoto University and Hiroshima University, something incredible happened. A team of researchers, led by the brilliant Professor Shigeki Takeuchi, announced they had solved a 25-year-old problem in quantum science. For a quarter of a century, physicists have been able to teleport the quantum state of a single particle, or maybe a linked pair. It was an amazing achievement, but it was limited. It was like learning to play a single note, when what you really need is a full orchestra. The Japanese team didn't just play another note. They figured out how to read the sheet music for the entire orchestra, all at once. Their publication in the prestigious journal Science Advances announced they had finally managed the first-ever experimental measurement of a bizarre and elusive form of quantum connection known as the W state. For decades, the W state was a ghost in the machine, a purely theoretical type of three-particle entanglement that was too fragile and complex to be reliably measured. But this team didn't just see the ghost. They built a machine to capture it. They developed a revolutionary device that can identify this three-part entanglement not through thousands of painstaking trials, but in a single, decisive shot. This is a historic leap. It moves us from fumbling with single particles to being able to identify an entire interconnected system as one cohesive group. It is the foundational first step required before you can even think about teleporting something truly complex. Now, before you start picturing starships beaming their crews down to alien planets, let's get one thing straight. Quantum teleportation isn't what you've seen in the movies. We're not moving matter. We're not disassembling a person atom by atom and reassembling them somewhere else. What we're moving is far more fundamental: information. Specifically, we are transferring the precise quantum state of a particle, its identity, its properties, its soul, if you will, from one location to another, without that particle ever physically traveling the distance. To get this, you have to wrap your head around the strangest, most mind-bending phenomenon in all of physics: quantum entanglement. Albert Einstein famously hated it, calling it spooky action at a distance. Imagine you have two magic coins that are intrinsically linked. You give one to a friend and keep one for yourself. Your friend travels to the other side of the galaxy. The moment you look at your coin and see its heads, you know instantly that your friend's coin is tails. No signal was sent, no communication had to travel through space. The information is just there. This is entanglement. Two or more particles become so deeply interconnected, they essentially act as a single entity, no matter how far apart they are. Quantum teleportation uses this spooky link as a cosmic postal service. Here's the gist. You have an original particle you want to teleport. Let's call her Alice. You also have an entangled pair. Let's call them Bob and Charlie. Bob stays with you, next to Alice, while Charlie is sent to the destination. You then perform a special measurement on Alice and Bob together. This action breaks the original entanglement between Bob and Charlie. But because of the spooky link, the quantum information that defined Alice instantly transfers to Charlie, who becomes a perfect replica. The original particle's state is gone, but its information is reborn in a new particle miles away. You haven't moved the particle, you've moved its identity. For years, that process worked beautifully, but mostly for pairs of particles, what physicists call duets. But the real world is a symphony. To build quantum computers or teleport complex systems, scientists needed to go beyond pairs and handle groups of 3, 4, or more particles all at once. And that's where they hit a 25-year-old wall. A profoundly difficult form of multipartite entanglement, known as the W state. If standard entanglement is like having two linked coins, the W state is like having three, but with a much trickier relationship. It's a delicate superposition of possibilities. Imagine our three particles are Tom, Dick, and Harry. In the W state, they exist in a quantum fog of Tom is excited while Dick and Harry are not, or Dick is excited while Tom and Harry are not, or Harry is excited while Tom and Dick are not, all at the same time. This shared state is powerful because it's robust. If one particle is lost, the other two stay entangled. But it's also maddeningly difficult to pin down. The old method, quantum tomography, involves taking thousands of measurements to reconstruct the state piece by piece. For the W state, this was like trying to photograph a soap bubble by throwing rocks at it. The very act of measuring one part would instantly destroy the delicate, multi-part correlation. For over 2 decades, the W state remained an experimental enigma. Scientists knew it was a key to teleporting larger systems, but it was a key they couldn't grasp. How do you measure a system where looking at one part destroys the whole? That was the puzzle that stalled progress for a generation. The team at Kyoto and Hiroshima universities, led by Shigeki Takeuchi, didn't just try to solve the puzzle, they changed the rules. Instead of measuring the W state piece by piece, they built a groundbreaking device that could see the whole picture at once. They created a novel method to identify the W state in a one-shot measurement, completely eliminating the need for destructive, repetitive trials. It's like being able to instantly recognize a chord in music, rather than having to identify each note one by one. Their machine is an elegant piece of engineering, but the real genius is how it combines stable optical circuits with a mathematical concept, the quantum Fourier transform. In simple terms, a Fourier transform breaks down a complex signal into its basic frequencies, like a prism separating white light into a rainbow. The Japanese team designed a photonic quantum circuit that acts like a quantum prism for entangled photons. When they feed their 3-photon system into this device, it doesn't just measure one photon, it analyzes the relationships between them, using the quantum Fourier transform to read the unique symmetrical pattern that is the telltale signature of the W state. This allows them to reliably distinguish between different types of 3-photon W states, something that was previously impossible. But the most crucial part might be its stability. Previous quantum experiments were notoriously finicky. This new device can operate stably for hours without any tweaks. This is a huge shift. It marks the transition of this kind of quantum measurement from a delicate lab curiosity to a robust, reliable technique. It proves that we can not only identify these complex entangled states, but we can do so consistently, paving the way for the real-world applications that will follow. The importance of this leap can't be overstated. Think of it this way. For 25 years, we've been working with quantum duets. We could handle the information of 2 linked particles, which is a neat trick, but it's not a symphony. A symphony isn't just a collection of instruments. It's the complex, interwoven harmony where the relationship between the strings, woodwinds, and brass is just as important as the notes. The W state is that harmony. It's the entanglement between multiple particles that carries a richer layer of information. By successfully measuring a 3-photon W state, the Japanese scientists have gone from being able to read the music for a simple duet to being able to read the sheet music for an entire string section. They've learned how to identify the complex, interwoven relationships of a group, all in one go. This is the very definition of scaling up. The ability to measure and identify these multipartite entangled states is the fundamental building block for any future technology that handles complex quantum information. A quantum computer, for instance, gets its power from the exponentially complex entanglement between its qubits. To build a network of quantum computers, you need a way to verify and transfer these complex entangled states. You need to be able to handle the entire orchestra, not just a few of its players. This breakthrough is the first time we've been able to reliably identify this kind of multi-part entanglement, proving that the principles can be scaled to handle the complexity needed for world-changing technologies. While the team at Kyoto and Hiroshima was cracking the W state measurement, other Japanese researchers have been exploring an equally fascinating frontier. Not just how to send quantum information, but where to store it. At Yokohama National University, a team led by Professor Hideo Kosaka has been doing pioneering work on teleporting quantum information into the heart of a diamond. Diamonds are famous for their incredibly strong and stable crystal lattice. Kosaka's team focuses on tiny, naturally occurring imperfections, where a nitrogen atom replaces a carbon atom, creating what's called a nitrogen vacancy, NV, center. This tiny defect acts like a nanomagnet. Using a wire about a quarter of the width of a human hair, the team can apply microwaves and radio waves to manipulate the quantum state of an electron and a nearby carbon atom, effectively turning this tiny flaw into a stable quantum memory. In past experiments, they have demonstrated that a photon's quantum state can be absorbed and transferred onto an atom, securely storing it inside the diamond. As Professor Kosaka explained, quantum teleportation permits the transfer of quantum information into an otherwise inaccessible space. This research is a vital step toward creating robust quantum memories, a necessary component for any large-scale quantum network. It shows that we're not only learning how to read complex quantum information, but also how to receive it and store it safely, opening the door for technologies like quantum repeaters that could one day form the backbone of a global quantum internet. So, a new way to measure a group of photons has been found in Japan. Why does this matter to you? Because this isn't just an academic victory, it's a breakthrough that enables the next steps for a technological revolution in computing, communication, and security. First, the quantum internet. Imagine a global network where your data isn't just encrypted, but is fundamentally unhackable. Because of entanglement, any attempt by an eavesdropper to intercept the data would instantly alter it, leaving a detectable trace. This Japanese breakthrough in identifying multiparticle states is a critical prerequisite for building the quantum repeaters and networks needed for perfectly secure data transfer. Second, this has huge implications for quantum computing. A major challenge is scaling up computers while maintaining the delicate entanglement between qubits. This breakthrough is a key step for distributed quantum computing, where multiple smaller quantum processors could be networked together. The ability to reliably measure and then teleport complex entangled states like the W state would allow these processors to work together as a single, more powerful machine. It's like networking brains together. And finally, the question on everyone's mind: what about teleporting people? Let's be clear. We are nowhere near beaming humans across space. The energy and data requirements are staggering, and we're talking about the information of a few photons, not the atoms of a physical object. However, this research is a genuine proof of principle. Before you can ever hope to teleport a complex molecule, you must first master identifying a group of connected particles. The work of these Japanese scientists represents that mastery. It proves that the foundational step for handling a complex, multi-part system is sound. While teleporting a person remains the stuff of distant science fiction, this breakthrough suggests that handling larger and more complex systems might one day move from theory to fact. We're living in an era where the line between sci-fi and reality is getting blurrier every day. These breakthroughs aren't just happening in movies. They're being published in scientific journals right now. If your mind is as blown as mine is by the fact that we are witnessing the dawn of the age of quantum networks, and you want to stay on the cutting edge of how science is changing our world, then make sure you hit that subscribe button and ring the notification bell. You won't want to miss what comes next. For decades, teleportation was a dream, a convenient plot device for storytellers. But the universe is a far stranger and more wonderful place than we ever imagined. The work of scientists like Shigeki Takeuchi and Hideo Kosaka at Japan's top universities has taken a piece of that dream and forged it into a tangible, technological stepping stone. They have solved a puzzle that stood for 25 years, proving that the spooky action that so troubled Einstein isn't a flaw in the theory, but one of its most powerful features. This isn't just a step forward for quantum physics. It's a leap forward for what we can build. We've moved from only being able to handle a single note to reading the music for a whole section of the orchestra. We're learning to send information into the heart of a diamond. We have laid the practical groundwork for a future of quantum networks, distributed supercomputers, and unhackable communication. The future isn't just coming. The blueprints for it are being drawn up in our present. And while we may not be beaming to new worlds just yet, we have successfully taken a first definitive step. We have proven that the principle of measuring complex systems is sound. And in doing so, we've shown that in the quantum realm, the only true limit is our own imagination. We are at the very beginning of a new chapter, and the question is no longer if these technologies will change our world, but when.